settled. So glad to have all of you and appreciate also that for many of you, this is either your last week of teaching or you are already kicking off summer and you're interrupting your summer vacation to do some professional development, which is pretty incredible. So go ahead and drop in the chat while everyone kind of gets settled your name, where you teach, what you teach, and the question I am most excited to see, where are you right now? I'm seeing some living rooms and dining rooms, but I'm really hoping someone is somewhere fabulous, like a mountaintop in Europe, and they have interrupted their hike to learn about water cycle and earth systems. Let's see where we're at. Home office, love it. Kitchen, always reliable, awesome. Okay, well, everyone's on the road. Yes. Hi, Julie, by the way, on the road. Fantastic. Relaxing, great. Okay, I'm hopeful that in your living room in sweats, comfy pants on, that is the best part about summer for sure, and just vacations in general. So glad to see it. Well, while everyone comes in and gets settled, I will start doing some kind of general intros and housekeeping, and then we're going to dive right in because we have so much content we're excited to cover. So let's just go ahead and get started. I am just going to kick us off. I'm Megan Morgan. I lead the Switch Classroom program at Switch Energy Alliance. We are based out of Austin, Texas. You can kind of see behind me, not wallpaper. I am in an office, but I have incredible Texas oak trees all around me. And there's often deer that come roam in the background. So it's as far as office workplaces go, it's a pretty great setup. But I'm here with my great team. We've got Jillian Sweats, who's running the slides, managing the chat. There will be follow-up emails and recordings. That all is Jillian. She's just the mastermind that handles all of that. But Switch Classroom also has a content team as well, and I know that some of our content writers from our Teacher Advisory Council are joining us as well. And so if I see them hop on, I'm going to give them a shout out. And then also we have our Colorado School of Mines guests helping us through the content today. These are our subject matter experts who are just going to dazzle us with all sorts of incredible information. But I'm going to let Alexis and Colin, I'm going to let you introduce yourselves, and then I'll do just a little bit more introductory housekeeping stuff while everyone, the last few people come in, and then we'll get started and we'll dive right in. So Alexis, I'll turn it over to you.
Great. Thanks, Megan. Hi, everyone. I am coming to you from my home office in Golden, Colorado, just up the street from the campus of Colorado School of Mines. I am also a little bit on summer teaching break, although as a researcher, I spend a lot of time doing research in the summer as well. But I'm really happy to engage with you all, the groups of teachers that are teaching our high school students and getting them ready and sending them off to college. So I'm a professor of geochemistry in the geology and geological engineering department. My research expertise is in the chemical interactions between fluids and rocks and minerals. And I'm going to be covering some of Unit 4. Unit 4 is kind of big, so I'm gonna cover a little bit of Unit 4 today. Oh,
Yeah,
and Colin, yeah, sorry.
yeah. Hey everybody, my name's Colin Sutton. I'm a postdoctoral fellow working with Alexis at Colorado School of Mines. I got my PhD from the
Have
University
a
of
hop
Wisconsin.
in, hop in.
Got my PhD from the University of Wisconsin about a year ago, so I'm just now getting my feet wet and teaching and doing things like that. Mostly spend my time researching right now and focus on physical hydrogeology. So I look at how water flows and how kind of particles or solutes are transported in the subsurface with the primary focus on energy systems, so like enhanced geothermal and carbon capture. And before I got my PhD, I worked in environmental consulting for a couple of years in Atlanta, Georgia. So I've done this kind of from the professional lens as well. And I will focus on the water cycle today.
Fantastic. So great. And Erica Erickson is going to join us in a little bit. She's actually running an APSI right now, which those of you who know APES well, that's the AP Summer Institute. So she's going to take a break from her APSI and join us to talk about all the wonderful ways that this content can be incorporated into your units that we talk about. Erica has been teaching for a long time. She's definitely a subject matter expert, SME, as far as it comes to the classroom, educational concepts, and certainly AP Environmental Science. Erica brings lots of experience, but also she brings a PBL lens to a lot of what she does. So she can feel free to ask her questions for any approach to AP Environmental Science, but I'm sure you'll see once she starts presenting that that is where she gets really excited. So we're glad to have her at the end. Just as a heads up, Erica leads a lot of our other AP Environmental Science webinars and workshops that we do at Switch Classroom. So if you enjoy her approach, and you enjoy her perspective, definitely stay tuned for the other AP Environmental Science events we do year-round, especially from about November through to March, when a lot of teachers are really in Unit 6, because Erica leans in and does a lot during that time. Okay, so just as we're meeting Alexis and Colin, and I've introduced Erica to you, just going to say one more time that Colorado School of Mines really are the subject matter experts. So Switch Classroom brings the instructional support. We often, we are the teacher down the hall, so to speak, for you. We like to provide resources that work that you can pull from a newsletter 5 minutes before class starts. If anybody teaches like I used to teach, that's full disclosure how I used to teach, is I had a general idea of where I was headed, but often came down to a couple minutes before the students came in to pull those last few things. So we create content to help you get through your day, to be the best part of your day, but we lean on our subject matter experts like Colorado School of Mines and our other technical experts to really bring and make sure that we are bringing you the right scientific information for everything we do. So we're excited about this series. We're going to do 3 of these this summer, and we'll have information further down in the presentation about how to sign up for those other ones. But this is part 1 of 3, and we really hope that you'll join us for the other ones. But we have a question for you as we kick it off today, just to get started. If you teach APES, and I understand you could be here and you don't have to teach in AP Environmental Science, but if you do, we have a question. What is your biggest challenge teaching AP Environmental Science? And I know for some of you, this is fresh. You just finished, you're just catching your breath. Maybe you came back from Cincinnati for the reading. For you and your students, what's the biggest challenge? I'm going to give you a couple minutes here. All right. Okay. And Jillian, I'm going to have you come off mute because, oh, there we go. Actually, I got it. It showed up for me. Thank you. All right, so you're seeing this too, a tie between student engagement or motivation and finding engaging hands-on activities. Certainly, definitely having challenges as well around access to high-quality, free, age-specific resources. And challenges around the real-world environmental and energy issues. Great. So great that we've got subject matter experts here today that can help us with that. And then Erica's going to wrap up by talking about a few hands-on things you can take from this presentation and just slot in your folder or your calendar for next year when you get there, and you'll have a great hands-on activity ready to go. So here's the big takeaways for today. Today you are going to walk away with, this is 90 minutes, well now we're down to 80 minutes, but you're going to walk away with a clear picture of how Earth systems and the water cycle connect. You're going to see how the soil systems and properties your students see in those multiple choice questions and data sets, and the FRQ strategies you can reuse for any systems prompt, right? So we're taking what we're learning today and we're giving you tools to be able to apply that across your entire year. Importantly, you're going to talk about with Erica the misconceptions that cost your students points on these units and how to get ahead of them. Some of you, and you can do a thumbs up if this is you, some of you are AP readers, and so you know how to prep your students for the test and the points. Some of you would love some support in that, and we've got you covered there. Okay, and then finally, like I mentioned, resources that you can use to pull into Unit 1, 1.7 specifically, and Unit 4, ready to use as is. But I should mention that every piece that we provide for you today can be edited, right? You can choose our resources as a PDF, or you can take it as a docx and just go ahead and edit as you need it. So if your students need some language support, some vocab support, some reinforcement in certain areas, you can add that in. All right, and I'm seeing we've got April Thompson, one of our Teacher Advisory Council members on. Hi, April, great to have you join us from Utah. Jillian, are you seeing anyone else from our TAC on here that we should give a shout out to?
We have Chris on here as well.
Chris Hill from Maine. Chris, glad to have you. Wonderful. If you're interested in joining our Teacher Advisory Council, you can find that information on our website. Our team is coming together this weekend in Austin, and we're doing a summer institute, a get together. We work, we play, we have a great time. So if you're interested, check us out on our website. But from that, let's talk just for a minute about how much these topics today, how much content that makes up on the exam. So the water cycle piece that we're covering today is about up to 8% of your student's exam. That's a pretty significant chunk. And then earth systems and resources, 10 to 15, right? Depending on the year. So together, we're looking at about 20% of the exam is covered in content today. So systems thinking now, when you introduce Unit 1 to your students, really does pay off for the whole year. And I'll just say too, let's do one last poll before we dive in and I turn it over to Alexis and Colin. Last poll question here for you. How confident do you feel teaching the water cycle and earth systems as part of the APES exam framework? About 20% of the exam. How confident do you feel? Okay. Few responses coming in still. Pretty good. Pretty good, but there's pieces you want to explain later. Perfect. Okay. So here's what we're going to do. We're going to kick this off with our partners at School of Mines. We're going to have the chat open. You can drop some questions in there. If there's topics or questions you have, we might jump in and answer them as Alexis and Colin are presenting. Or it might need a little bit more time and we might save it till the end to talk about. Now there's a possibility that we just get so excited and we keep sharing and talking and discussing and we don't get to every question, and in that case we're going to gather those up and get answers for you and include that in the mail out afterwards. So after this presentation, the recording will be available within a few days. It will be available on an unlisted YouTube link, so you can find it there. We'll also send out the slide deck, and we will send out any unanswered questions, follow-up resources, things like that. Will come to you within a couple days. So if you have to hop off because the sun is hot and you've got kids at your ankles, we get it, and we'll follow up with the information for you. We would love for you to stay to the end. We've got good stuff all the way through. Oh, Alexis, thank you. Alexis just dropped her email. If you've got additional questions, you can follow up with her. So that being said, let's go ahead and dive in to the water cycle and earth system resources. I'm going to turn it over to you, Alexis and Colin.
Awesome. Thank you, Megan. And I will start us first with the water cycle portion, Unit 1.7. And for this, we're going to talk about really all aspects of water on the earth, that being from oceans to the freshwater we think of typically, and things like ice and glaciers, as well as groundwater. I don't know if I can control the slides or how that works, but Okay, so if we think of the water cycle, we can think of these kind of Department of Interior or USGS water cycle maps that we commonly see with this. And this is water that we typically think of, things that we can see on a daily basis. So things like our oceans, our rivers, uh, things like lakes, clouds, stuff like that. And the way that we want to think about these are in terms of storages and fluxes. So when I say storage, I mean somewhere that water is going to be stored for long periods of time. So you can think about a lake, reservoir where we hold water for municipal supply, oceans, groundwater, things like that. We call these storages or reservoirs. And then fluxes is the second part of this. So this is when we have water in motion. So this is, we can think of it really anywhere that water is in between two storage points. So we'll go into the fluxes pretty heavily here. And a big thing to remember about all of this is that the water cycle is really powered by energy from the sun. So the energy, typically in the form of heat, and when we're thinking about the water cycle, is really what's powering this whole system. So if we move on to the next slide, what we can see, I don't know if I have control, is the global water cycle. And then what do we think of as these major storages? So these are going to be things like, we click again. Oh, sorry. Yeah, that's fine. So the storages are things like oceans, groundwater, lakes, things like that. And in terms of global water volumes, the ocean is going to be our largest storage or our largest reservoir. However, it's all salt water. So it's not necessarily useful in terms of what we think of for human impacts or human uses. So the ocean is going to be about 96 and a half, or roughly 97% of our total water on Earth. So if we think about this in terms of Olympic-sized pools, if we had 100 Olympic-sized pools, 97 of those 100 would be salt water from the ocean. Then we can move on. And then the fresh water is the rest. So this is the other three pools that we would have. The majority of that is going to be in glaciers and ice caps, about 60% of the fresh water that we have, and then the rest, the majority is going to be groundwater of what we can actually access and use, followed by rivers and lakes, and then lastly, water stored in the atmosphere. And for those actual numbers here, so if we look at this, again, 97% of the water on Earth is going to be in oceans, but again, there's 0% of fresh water there. The glaciers, ice caps, and snowfields comprise 69% of the fresh water. And then the groundwater, what we can access the most easily, is going to be about 30% of our fresh water. And then lakes and rivers comprise a very small portion of what's left. And then again, if we want to think about what the volume of water is, kind of in a general term, this image really shows you that oceans are the majority of what we have as water on Earth. But again, this is going to be salt water. Groundwater, ice caps, and glaciers are by far the next largest set, and this is all freshwater. And then other freshwater, again, like rivers and lakes, is going to be just a very small portion of the surface or of the freshwater that we have on the Earth. And the majority of the accessible water that we have will be in soil and rock as groundwater. So then if we go back to this water cycle image, remember I said that we're thinking in terms of storages and fluxes. Uh, the major fluxes that we have here, if we click one more time, are going to be what I'll call the hydrologic cycle or the hydrologic processes. So I'm going to split this up into hydrologic and atmospheric processes. So the major fluxes for the hydrologic processes are going to be precipitation, surface runoff, snowmelt runoff, stream flows, infiltration into the ground, and then groundwater flows themselves. So precipitation is the first one of these, and precipitation is the release of water from the atmosphere that will eventually reach Earth's surface. And a key point to take away from this is that rain is one of the forms of precipitation and is the one that we maybe most commonly think of. However, it's not the only one. We also have sleet, hail, and snow that are precipitation as well, since they're the release of water from the atmosphere. And then the next one that we're going to have is snow melt. So once we accumulate snow on the ground, this is storage in and of itself because it sits on the surface until it can melt. Once it melts, we have what we call snow melt, which is the transition of solid water to liquid water. And this manifests itself as surface runoff. And you can see that in the image on the right here, where you have snow stored on the surface, and then as it melts, that snow will run off to some other place. And this is seasonally dependent. And once again, this depends on the energy from the sun. So you can see in the plot on the bottom left here that this happens, at least in the northern hemisphere, towards the end of winter or spring as temperatures start to warm up and we can melt the snow into liquid water that will then run off. So the next one that we're going to talk about in terms of hydraulic fluxes is surface flow. So this is very similar to that snow melt runoff, except for this type of flow typically comes from things like precipitation. So this is where we have actual water that's running on the surface of the earth. And you
Sit
can
down.
see kind of
No.
yeah, so you can see in this image, this is where we have something like a ditch in a field where water goes to that point, kind of flows downhill, and we get uh, kind of large amounts of water running off quickly. And this is important because this prevents water from going into one of our storages, being groundwater, and it funnels it someplace differently. So we're typically maybe familiar with this in terms of overland flow or runoff or flooding is what we hear a lot in the news when we have a lot of surface flow. So then, as I mentioned, the thing about surface flow is it moves water very quickly from one place to the next. So we skip this step called infiltration. Infiltration is when the water moves from the surface into the soil and then eventually into the groundwater. So you can see on this image down here, as precipitation comes down, if it hits the surface of the earth, you have infiltration or runoff. So infiltration will go through the soil and either sit kind of in that layer of soil or start moving towards the river or eventually go into the groundwater, which is what we call percolation. As the water gets into the soil and starts to move through it towards the water table, we have percolation through that unsaturated zone. And these are all important aspects, how we move water from one storage place to the other. And then for groundwater flow, this is kind of our last flux in that image that we saw. And this is going to be the movement of water throughout the subsurface. Typically is always going to be below the water table, and that's what makes it groundwater. And you can see on this image here, this kind of puts a lot of these things together where we have precipitation that hits the land surface. That precipitation might run off on that stream that we see, or it will infiltrate into the soil where it then percolates and is either intercepted by things like plants, which will go into our atmospheric fluxes, or it goes into the water table and then becomes groundwater, which then will flow to some other place and is in flux at that point until we hit another storage. So the last thing to really talk about here is kind of this groundwater surface water interplay. And what you can see on the left is what I'm calling a natural condition. So this is where everything is kind of happy with each other. Precipitation hits the ground, it infiltrates and percolates into the groundwater, and then it flows into what we call a gaining river. So this is a river that's getting its water from the groundwater itself. So that river will typically stay kind of flowing as long as the water table is at the same level as the river. And then in this other condition, what I'm calling a stress condition, is where the groundwater, the kind of this water cycle is not really happy. So something's changing the dynamics. In this case, it could be a drought. So things are dry and we're not getting a lot of precipitation that kind of lowers the water table naturally. Or we can have something like a well where we get this cone of depression around the well. So where the water table is being kind of artificially drawn down due to pumping. So as this draws the water table down at that point, kind of the hydraulic head or the gradient in pressure will make water actually flow from the river down towards the groundwater table instead of feeding the river with water. So in this case, we might actually have a scenario like you see out west a lot where the rivers aren't there all the time, and it's kind of dependent on how much rainfall or precipitation surface runoff that we get. So then from there, we'll talk about kind of the next set of fluxes and what I'm calling atmospheric processes here. So these are things that directly give water back to the atmosphere. So we're talking evaporation, evapotranspiration, which is the combination of evaporation and transpiration from plants, fog and dew, sublimation and desublimation. And again, these are all powered by the energy from the sun. And then the first one of these that we will talk about is condensation. So condensation is the transition of water vapor to liquid water. So this is things that we see pretty commonly if we think about what's happening outside. So things like clouds or fog. And the way that this happens is actually from cooling of warm air or when water is oversaturated in the air. And the cooling of warm air can happen most commonly by the warm air rising in the atmosphere where it's cooler. And when this happens, the temperature at which the water vapor transitions at the dew point causes water to leave the gas phase. And then the next flux here is evaporation. So this is the transition of liquid water to water vapor. And this is powered on Earth's surface by the sun's energy, so heat. And this happens when hydrogen bonds between water molecules break and turn liquid water into water vapor. So this happens kind of at all temperatures, but where we're probably the most used to seeing this happen is if you boil water. As you get the water towards the boiling point, you break a lot of hydrogen bonds, and then you can see the evaporation or water turning into liquid water turning into water vapor. And the kind of the important thing about evaporation here is that this is actually where 90% of moisture in the atmosphere comes from. So the majority of water returning to the atmosphere and then feeding cycles like precipitation is coming from evaporation of water at the Earth's surface. And then from here, the next one that we'll talk about is transpiration. So transpiration is going to be the release of water within plants to the atmosphere as water vapor. So this is kind of how plants are breathing in their kind of natural respiratory process. And the majority of the rest of the water in the atmosphere is coming from this process. So again, about 90% of the water in the atmosphere is evaporation. A majority of the rest of it, of that remaining 10% is going to come from transpiration. And these commonly combine evaporation and transpiration into a single flux called evaporation. So mathematically you can combine those two, the evaporation and transpiration, to account for this water balance of in and out fluxes. And then the last one that we'll talk about here is sublimation. So this is by far the least common, but if you're familiar with either high altitude or very cold environments, this can be a part of the water cycle. And this is the transition of solid water to water vapor. So it completely skips the liquid phase, and this only contributes a very small amount to how much atmospheric water we have. And this typically happens when we have very favorable conditions for sublimation, so low humidity and dry winds. So this happens very often on like the frozen lakes in Canada or the far north in the US during like the Arctic blast, where it's very dry and very cold, and water will go from the solid phase, ice, to water vapor. And again, this is more common at higher altitudes. And then there's a lot of us here, so I won't really go into asking for any answers here verbally, but take a look at this water cycle diagram and see if there's anything that's missing from what you think that we should see in our water cycle. So we have everything that we've talked about: precipitation, condensation, evaporation, all of our fluxes, and all of the surface and groundwaters. But one thing that we're missing is human activity. So if we go over to the next slide, our water cycle diagrams don't often show what's happening in terms of human activity. So we see kind of these natural processes, the pristine looking lake environments, mountains, oceans, and things like that. But what we miss out a lot on these water cycle diagrams is what humans actually do to this water cycle, so our anthropogenic effects. And if we just take a look at this diagram, and it's not the highest quality one in the world, but you can see in the middle we have domestic water use and disposal. So this is, how people are withdrawing water. So think back to that aquifer diagram where when we withdraw water, that changes the water table and how water's flowing. And then we have agricultural water use and runoff. So we do a lot of irrigation from groundwater and things like that. And then when we build our cities, we change the surface cover from soil and grass and natural environments, things covered by concrete, which change the how water flows on the surface. So that changes our runoff patterns. So a lot of times we don't think about this with the water cycle, but human impacts are can be somewhat significant. And that's where I left it off for the water cycle stuff. So if we have any questions or anything later about human activities, we'd be happy to answer that.
Okay. Let's see. Click to start the remote control. Awesome. Any questions about water cycle before we jump a little bit into soils and weathering? You can put it in the chat if you want. Okay, I think we will keep going. I was looking through Unit 4 and I decided to focus on soil formation, erosion, and soil composition and properties, in part because it connects so well with the water cycle. And so you're going to see some of the same concepts that Colin just talked about in the water cycle show up as we talk about what happens with soils and what happens with weathering, and what we think about in terms of the way that soils work and their importance. Let's see, next slide. Okay. So rock weathering isn't explicit in Unit 4, but I wanted to bring it in as a place to start, not only because it is my favorite topic in the whole world, but also because it is really the place we think of when we think of the start of soil formation. So on the left-hand side, you can see an image, just depicting bedrock at the bottom, some weathering interface where that bedrock is interacting with water that has infiltrated from the top down into the soil and then down into the bedrock where it becomes groundwater, and then all the way up to the top where we've got plants growing on the top of this hypothetical column. This happens on all scales, on all surfaces. And when we put that in a watershed context, which is what we have on the right-hand side, and I know watershed is one of the topics, you can see that we could have different slopes for the surface, the land surface of the watershed. We can have different amounts of water that the land surface is seeing, different amounts of water that is, infiltrating down into that subsurface to drive weathering. We can have erosion up in the high peaks. We can have water ponding and sediment transport and collection in the low valleys. And all of this happens within this, what we call the watershed divide, which is actually a surface expression definition, which is that if a droplet of water falls on the land surface and all collects in the same river system, that is all part of the same watershed. And so that dotted line represents a line on the land surface where any water droplet that falls on the surface would drain into this small pond or lake that's at the front of the diagram on the right-hand side. And so when we think about weathering and we think about soil development, it's happening everywhere all the time, so long as landscapes are stable. And we'll talk about that. And then, do I have remote control, Jillian? Are you okay? I'm not sure how to make it go. Okay. Oh, maybe it's just slow. Maybe that's why. Okay. I'll be a little more patient with my clicking. So this weathering that happens when water, lands on the land surface and infiltrates down in and comes into contact with rock in the subsurface that's out of chemical equilibrium, and just starts to dissolve that rock away. And it's a slow process, and not a lot of rock dissolves into each, small volume of water. So 1 liter of water doesn't dissolve a whole lot of rock. But it dissolves enough that it puts these solutes into solution. So the groundwater and the soil water starts to accumulate the things that are in the rock, like potassium and phosphorus and calcium and magnesium. And so in my depiction here on the left-hand side, you can kind of see this tree growing on this land surface, and you've got bedrock on the bottom, and then you've got this saprolite here in the middle. Saprolite's just a fancy term for weathered rock. And you can see some of the aspects of the water cycle that are important here in that you've got, rain that can come down on the surface, and then that can create groundwater, and then it can come down and, sort of flow shallowly through the subsurface, like these big blue arrows show, and take that water out to the stream. Well, that water that collects in the subsurface in our soil and our saprolite is then also available to plants, and plants will take that water up and they will transpire it, and that's part of the water cycle. But then that water is not just water anymore. It's actually water with solutes in it from that reaction, the chemical reactions between the water and the bedrock. Those solutes are nutrients for vegetation. And trees and plants actually actively harvest some of these nutrients. So they put organic acids into the subsurface. So they're not just a passive consumer of the solutes that are made by weathering. The plants will actually actively promote weathering in the subsurface because it gives them nutrients. And so this is, kind of a two-way street here. And so you can see that, we've got primary nutrients, secondary nutrients, and micronutrients that come out of the soils. In particular, the micronutrients are important when it comes from bedrock weathering. And then on the bottom pie chart, what you can see is kind of an average composition of the chemistry of streams. And so the solutes that actually gets into the streams without, being consumed by the plants. And that's the stuff that accumulates eventually and ends up in the ocean. And so weathering controls the chemistry of oceans over really long time frames. So that's kind of the place that, when we start to think about soil development, we start to initially think about this idea of weathering of, whatever is, making up, the bedrock. Sometimes it's not even rock, it's actually just sediments, but whatever that primary material is, then you start to weather that, you start to release nutrients, you break the rock up, the trees can grow into it. The trees become an active participant in that weathering process. Their roots are breaking things up, and the trees are actually promoting weathering so that they can gain access to those nutrients. So with that as a background, then we can start to talk a little bit more about how soils form. So weathering then breaks these rocks down into smaller particle sizes that can be transported through erosion. So this sediment that gets created through the process of weathering can be transported by water in rivers, can be transported, in the air column by wind. It can be transported by ice in glacial systems, and it can be transported by gravity, which is really, landslides and mudslides and things like that. And so when we think about the material that soils form on, it doesn't just have to be the idea that soils are forming on just bedrock. Soils can actually also form on transported material. Let's see. Okay. And so any sediment that stays in place for a long time will turn into soil. And any bedrock that's in place for a long time will turn into soil. And we talk about these soil forming factors. I think in the AP materials, time isn't really included, but I always include time because something has to be in a long place for it to turn into soil. So water has to infiltrate, things have to grow, we have to accumulate material, and all of that just takes a really long time. And so the other four things that we talk about are the parent material. What's the stuff at the bottom of the soil that the soil is actually forming on? Climate, how hot is it? How much water is available? How much water is falling on that land surface? Topography, if it's really steep, then sediment's not going to stay there really for a long enough time to start and really promote that soil forming process. And so topography plays a really strong role in how much time you have to actually form a soil. And then the biologic activity, I said, right, it's not passive. It's the biologic activity is actually, an active participant in the soil forming process. And I noticed that Cedar posted in the chat that a common student misconception is that weathering and erosion are the same thing. And that's true. And we see that in, the college students that we have is that, weathering and erosion are the same thing. So weathering is really the chemical breakdown or the mechanical breakdown of a rock into smaller pieces. And erosion is taking those smaller pieces and moving them somewhere else. So we actually have two different forms of weathering. We have mechanical weathering and we have chemical weathering. Chemical weathering is my favorite, but we can have mechanical weathering too, through rockfall, where rocks just break apart through physical forces. But then the minute you take anything that's broken apart and you move it somewhere else, that is what we think of as erosion. See. Okay, so if we think about, right, this parent material, we can have parent material that is from primary intact bedrock. Oh, that didn't, okay, that's fine. So this is a metamorphic rock that you can see on the right-hand side here, a hammer for scale, because as a geologist, we always put a scale in all of our photos. But any primary intact red bedrock can be the starting place for the weathering process that then breaks rock apart, that then provides the sediment for us to actually weather on top of. Transported sediment, often, we think of transported sediment by wind or by water. In this case, we can have dunes that are created and, floodplains, and then that sediment, sits for a long time and starts to turn into soil. A really interesting aspect of soil in the US is that most major crop areas correspond to transported sediment. So soils that are formed on top of transported sediment, not formed on top of in-place bedrock. So on the left-hand side, this is just for winter wheat. And so you can see the colors show major crop areas and minor crop areas. And on the right, I have a pretty simplified map of aeolian sand and loess deposits, which is transported by water, sometimes by wind. And you can see where those are in the continental US. And these two are pretty spatially correlated with each other. And so this loess that makes up the majority of the Central High Plains actually all came from one source. It's called the Peoria loess. There's different portions of it. And it all came from the Laurentide ice sheet. Or the melting of the Laurentide ice sheet and the dry conditions to the south of the Laurentide ice sheet, which promoted a bunch of sediment blowing around. And so this was during the last glacial maximum. So on the left, you can see the furthest extent of the Laurentide ice sheet about 20,000 years ago. And then you can see all these deposits of the Peoria loess to the south of that, either transported down the Mississippi River through a lobe that's, kind of along the Mississippi, or off into the plains where there was a lot of glacial damming that broke, sending big glacial floods out that carry all of this sediment that was trapped in the ice as it melted and, sourcing it out, and then a lot of wind. So you can think of this area as being really dry and cold and windy at that time. And so anything that did come out in terms of the sediment and get deposited and dry out just became, sediment that blew around a lot. And that became really fertile soil for today's modern agriculture. So let's move on to climate as a soil forming factor. And so what you can see here on the right-hand side is a map from the National Soil Survey Center. So they have a lot of really great visuals around soils and soil types and climate as it impacts soil. So this is a map of soil moisture regime, that what they call soil moisture regime. And there's lots of different ways to classify soil. But what you can see is that there's a very strong correlation here, spatial correlation across the continental US. So on the right-hand side, we've got mostly what are called eutick soils. So there's enough moisture around. Things are typically, you've got enough water moving through the soils to promote soil development, and those waters and those soils are, they have a lot of moisture in them a lot of the time. On the left-hand side here, we have soils that are very, very dry. So in the reds and the oranges, these are called xeric soils, xeric aeritic soils. And so these are very dry soils. And very dry soils are characterized by the precipitation of salts. So calcium carbonate, and so you get these salts precipitated into the soils, and that actually limits their fertility in some cases and their ability to retain soil moisture. So this climate aspect of soil formation is very strong. So the warmer it is, the wetter it is, the more you're going to promote biologic activity, the more you're going to promote breakdown of organic matter and the rocks themselves and really push that soil formation forward. So in the absence of a lot of time, we can actually have warm, wet climate. So time and climate go hand in hand because it really is just about, kind of how much, water you can push through and promote that soil formation. And so I'm not going to talk, in great detail about topography or biologic activity. We've already covered those a little bit, but topography really is related to time in that if you have steep slopes, you don't retain sediment on those slopes, you don't retain weathered material on those slopes, and you just really can't have a lot of soil formation. So the time aspect of this, and this is kind of the idea that maybe we're starting with, this bedrock over here on the left with an immature soil. The rock starts to break up. You get water filtering down through cracks, fractures, and that promotes the breakup of the rock and the conversion of the primary minerals in the rock to clay, which then can help create soil. That clay holds on to water, and so that water kind of stays around a little bit longer. And you get the first kind of biologic activity here often is moss and lichen growing on top of those rocks. Again, those moss and lichen aren't passive. They're actually actively creating a weathering environment to promote the breakdown of the rock to get the nutrients, and that promotes soil formation. And then we move into a young soil, which is going to have, often grasses and small shrubs. You've got, more broken up rock in the top, the grasses and the small shrubs. They have roots. They're going to put organic acids and humics into the soil, and you're going to accumulate organics in the top of that soil. So this is really when we start to, build up the organic debris in the top of the soil. And then over time, you really develop a complex ecosystem in that soil. So bacteria, we still have fungus, which, lichen is a kind of fungus. So we've got bacteria and fungus living in the subsurface. And then we have rooting trees and bushes, and those rooting depths get much deeper at this time. So in a mature soil, the rooting depth is much deeper, and the soil itself can hold more water. And so then when you have soils, they're really characterized by 5 different horizons, and not every soil has to have all 5 horizons. That's also something that's kind of, I think, a misconception is that every soil has to have all 5 horizons, and they don't. And so you have horizons, and when we go out and we identify and we describe soils, we describe the ones that we see. But when you do have these horizons, this is the order you find them in. So the O horizon on top is really the partially decayed organic matter. So it's the fresh stuff on top. The A horizon below that has maybe some mineral matter, and it's got this partially decomposed organic matter. And we call that humus or humic acids. Below that is sometimes present an E horizon. And an E horizon, it's called the E horizon because of this term alluviation, which is really just meaning you're taking material from that horizon and moving it down through the profile. So you're leaching out of that horizon. And if you have enough leaching, you're going to leach iron out of that, which is what then bleaches that layer. So a well-developed E horizon has lost actually a lot of clay and a lot of iron. And we really only see this, especially in the US, like in the southern Piedmont, where we have a lot of water and high temperatures. And so places like, where we are in the Rockies, we really don't get a lot of E horizons. We don't have enough water for that to happen. And then the B horizon is just the accumulation of the stuff from the A horizon and the E horizon. And so we're moving that stuff down. This is often a very clay-rich layer, kind of light brown to dark brown, and it sits right on top of the C horizon, which is loose and partially altered parent rock material. And then again, this parent rock can either be rock or it can be sediment. And so these 5 different horizons are characterized by how much clay they have, what their chemistry is, how much water they hold, and a bunch of different other things. And so what that soil is made of is, different particle sizes, and we think about soils as having texture. And that texture is mostly determined by the particle size. And this soil texture diagram, I think, shows up fairly regularly on the AP exam. So we love trilinear diagrams in geology. It gives us a way to take and look at different kinds of systems at different scales and rescale them all into a classification where we have kind of three end members. So here we would have a clay end member, a sand end member, and a silt end member. Clay, sand, and silt are just defined by the size of the particle. So clay is really, really small, less than 4 microns. Silt, 4 microns to 60 microns or 0.06 millimeters. Anything, between silt and 2 millimeters is what we would lump in with sand. And then we don't really include the gravel aspect of soil in this textural classification. And so really this trilinear diagram is just a way to renormalize these three components to 100%, and then you can plot them and then read off the soil texture. And so soil texture is important because it determines a lot about how that soil holds onto or transmits water. And so we've got drainage. So soil texture then is a primary control on what's called the water holding capacity of soils. So sand has a low water retention, a low water holding capacity because it just drains right through. The water is just going to have lots of pathways and it's going to drain right through it. On the other side of that, we'll go to clay next. Clay has a high water holding capacity, in part because clay particles themselves hold on to water. And so clays have this ability to really retain a lot of water and release it very slowly. And then in the middle, we have silt, which can hold water, and it's got, moderate retention because the pathways through silt are smaller. And so that water just takes a longer time to get through. And so really a good soil for agriculture purposes to hold on to water is some mixture of sand, silt, and clay. And that really gives us both the drainage so that we don't waterlog the soils, which then decreases the oxygen, which plants need oxygen, microbes need oxygen. And so we need some sand to promote drainage, but we need some silt and clay to hang on to water so that that water is available to plants in between periods of precipitation or watering. And so the combination of those three is really important. Another thing that's really important is whether your soil is compacted or not. And so soil that has lots of pathways that go through it and roots can make pathways, what we call macropores, are really good because you get air and water, and you need both air and water in your soil to promote biologic activity. And so when a soil gets compacted, everything kind of gets smashed and we can't get moisture or air in there. So tilling is one way to break soils up. And when we think about what we do in our lawns, we call that aeration. And so a lot of people, who take care of their lawns will have someone come aerate their lawns, and you get these little plugs that they pull out and, push off to the side. And it creates these pathways for water and gases to get down into that root zone to then promote the rooting growth. Those roots promote their own aeration because they break those soils up, and that promotes more water and oxygen in there. So this idea of soils, weathering, water cycle, they all fit really well together, even though they're cut across two different units in the APES content. But the threads through here between water and soil and agriculture are very strong, and that is the content I have.
Fantastic. Thank you, Colin and Alexis. And Colin jumped in the chat and I put a little muscle emoji because he definitely brought the brain and the brawn for that one. So thank you. Before we jump and talk directly about resources in the classroom and how students see this on the exam, Alexis, you teach a lot of introductory courses. Thank you both, by the way, for great content, but really presented in a way I think that tells a story, which is helpful for all of our teachers. What do you see when you see intro level students coming into your classes? Do you see some big misconceptions they're coming in with that either surfaced throughout the course or over the years you've recognized and had to sort of address at the beginning?
I think well, actually, the idea that weathering and erosion are the same is one that we definitely see. So we see that one. Um, I'm trying to think. Really, I guess the other thing that I think we see, which is a bit broader, is that I teach, it's in the geology department, but it's Earth and Environmental Systems is the name of the class. And what I see a lot of is, the misconception that geology is just rocks. And, environmental science is, all about human contamination and keeping the environment clean, when really those two things are, basically just, slightly apart on a continuum of the study of earth science and earth systems. And so a lot of times I get students who think, I'm really interested in the environment, but not geology because, geology is all about, going out and hiking and, taking oil and gas out of the ground. But I have a geology degree. Colin has a geology degree. So, we have a big wide range of things that we do as geologists, earth scientists, and environmental sciences. And it really is, a lot of times it's just the different piece of the earth system that, we spend most of our time thinking about.
That's great. Thank you. Colin, I don't know, do you have anything to add to that?
Yeah, I have one I can throw in just more as a hydrogeologist. The thing that I think I've seen most is that it can be hard for students to conceptualize what exactly we mean by groundwater until they have like seen like maybe a model, like a sandbox model or something. Because we can't really take a picture of groundwater because it's underneath the earth. Like a lot of people will come in maybe thinking the groundwater is like flowing water underground, like a lake, like what you might see in a cave. And like that exists, but it's relatively rare. It's usually kind of what Alexis has been showing here with water in pores or water moving through cracks in rock. So that's kind of a big one is kind of this idea or conceptualization issue of what we mean by groundwater because it does move through rock, which can be a little difficult to think about.
So great. Perfect. Okay. We, I was hearing from a lot of you throughout Alexis and Colin's presentation that you were just eating up the diagrams and the maps. And so what we were going to make the slides available anyway, but we're going to make sure that any sources that need to be cited on there get added. And then also that the School of Mines logo is on there because that is certainly their content. And then we'll PDF it and help you use those in your classroom. Alexis and Colin, if that sounds like a good plan, we can chat through any details afterwards, but we certainly want you to be able to take this information and maybe add to what you have in your current resource buckets, or tool belts, I should say, or maybe you've got some gaps and that's where some of this content can slip in to clarify misunderstandings or to just really bridge concepts that you haven't had before. Go ahead and keep adding your questions in the chat. I know that Alexis and Colin are monitoring that and commenting when they can. And I know Erica just hopped on. Hi, Erica. We also have Chris Hill, who I didn't introduce beforehand, and April Thompson. I'm going to let them introduce themselves because they are also AP Environmental Science teachers. They're experts on our team. They host webinars and whatnot as well and do workshops. And they are able to comment as Erica's going through here to fill any sort of other ideas and impressions. So Chris, I'll turn it over to you to do an introduction, and then April, you're next, and then Erica, you're up.
Hey everybody, my name is Chris Hill. I'm a teacher at Yarmouth High School, Yarmouth, Maine. We just finished our school year last week, so I'm kind of on my first days break. And yeah, thanks Alexis and Colin. Loved your presentation and had some really good diagrams. Particularly, I love when you put kind of two images up and ask students, what do you notice? What do you wonder? it's just a great exercise to get them thinking about those patterns. So thank you.
April.
Hi everyone, I'm April Thompson. I teach at Westlake High School in Saratoga Springs, Utah. And what I love about this webinar is seeing how they tell a story with multiple concepts. If I could say anything about environmental science, which I think they've done a great model for, is that teaching the concept in isolation won't get the kids where you need them to go. It's how is everything connected? And I think they did a great job of modeling how you can bring so many content ideas together into the story of the water cycle or the story of soil. And that's really going to help the kids progress. So that was perfect how they did it. So hands 10 out of 10. That's what I'm trying to say.
I agree. Okay, Erica, I gave you a little introduction at the beginning. I hope your APSI is going well. Thank you for stepping out to do this. We're excited. We've got probably 15-ish minutes, Erica, maybe 20.
Perfect.
So I'll let you take it from here.
Okay. It's
And
going to look
we'll
like
be
a
watching
lot.
the chat.
Okay,
Yeah, we'll be watching the
fantastic.
chat.
Thank you. Yeah, let me know if there's any questions. Thank you all for allowing me to come and do this with you today. So I've been teaching at APSI all morning. I'm admittedly a little tired, and so, but it's going well. So let's get going on this. So my name's Erica Erickson. I teach APES and physics and AP Bio in rural North Georgia, and I'm happy to share this with you. So next slide. Okay, so this is kind of where we're going. So we just had this crazy, and I missed it, which I'm sad about. I'm looking for the next two now, but you just heard all this content information. And so if you didn't already realize it, APES is concept heavy. So the question that I'm posing to you guys as a guiding question for the rest of my time with you is how do we as APES teachers balance teaching the required core knowledge with the teaching of the exam expectations? Because we have to teach the exam as well. We can't let them go cold into something that is potentially college credit. And so what I'm going to do with you guys is like, okay, so we just had some required content. Fantastic. Obviously, you need to figure out where and when and how you're going to embed the practice to get your students to understand and be comfortable with, more importantly, um, how to conquer that exam because it's long and it's complex in terms of the way the questions are being asked. And there's multiple choice and free response. And the free response is on the computer and they have to type it. And the free response includes math questions and they have to type in the math notation. And right, what in the world? And so there's a lot to kind of take in here. And so embedded with the FRQ, besides teaching them to understand what you're looking for, how to get that point for all the questions, you need to teach them the task verbs. And the task verbs are extremely important, I think are overlooked, especially by new teachers. And if you don't teach your students what the task verbs are, they won't know how much to write and they might lose the point. We're also going to talk about math a little bit. Next slide. Okay, so the first thing I want to go through, and we're going to go this quite quickly, and literally just kind of enough to see the graph itself to remind you what they are. You guys, I'm sure everyone will get this sent to them, and so you'll have this, and you can go back and review at your own leisure. And so these are the graphs and charts that you need to know, what your students need to know, and so you need to make sure that you're teaching them. These will be on the exam. These are highlighted in the CED as things that will be there. So for ecology, obviously exponential growth, logistics curves, carrying capacity, overshoot. In terms of population, survivorship curve, age structure diagrams, demographic transition. No one ever teaches that well enough. We always kind of skip over that one a little bit. Land use, half-life curve, and the soil texture triangle. And some of these you saw today, but very quickly, let's click through some of these pictures and just leave enough time to like, yep, there's your J curve, right? We got that. There's our S curve. Here's a little bit more on the J curve that includes the dying period. Oxygen side curve. R and K selected survivorship curves. Here's our population pyramids. The demographic transition. The decay of radioactive substances. And then there's our soil texture triangle. Okay, so one more slide, please. Okay, so that's a lot, right? And so you guys can go and explore those. You can use those pictures if you'd like to, but your kids could be given questions, MCQ or FRQ, just about those pictures, having to interpret them. They could be picture free, and then it could be the concept itself that they have to kind of imagine. They might need to draw something out based on a chart. So what does it actually look like in terms of how do we get your students to be prepared for this? Well, there is some resources that have been created by Switch to help you guys carry this through. So this is a complete curriculum and study guide for the entire AP Environmental Science course. So if you're interested and you want to pick and choose, and this is an editable doc, all of the stuff from Switch is editable. If you want to go in and pick and choose and figure out what's going to work for you and your students, then this is a recommended resource if you have some holes that you're trying to fill or trying to do something better, because this will help you get to the right place. Next slide. There's also, in general, just a resource collection, and this is all of our APES aligned resources. So that was just this curriculum, but there's more than just that, guys. Don't forget that there's anything from videos to bell ringers to quizzes to labs to you name it, it's there. Go and look for it, right? One topic that you'd love a stronger resource for, if you guys take a moment, just off the top of your head, what's a resource that you think that you'd benefit from having a little bit more information about, or a way to instruct your students? If you guys have some time to do that after I keep going, then please keep adding them because we'll look at them and see what we can do. The nice thing is that we've got some math practice. I'm going to show you that at the very end of the presentation. So good. So Unit 9, okay. Yeah, I agree. Yep. I mean, climate change is happening now, is it not? There's a heat dome over France right now, guys. So yes, yes. So wind patterns. So there's a lot of stuff here that could be created. Okay. So I'm going to move on. You guys have some, this is a far-reaching range of ideas here. Some of this we do have, and some of it that can be created for future use. Okay, so let's keep going. So the APES exam format, if you weren't already aware, and I think that some of us forget, please make sure your students are exposed to this. You may want to make a poster for your wall, right? So the multiple choice is 90 minutes. If they go over 90 minutes, it shuts off, right? There's 80 questions. And so it's about 1.23 minutes per question. I would emphasize that because what that means is they need to use their resources. And so they read a question and they have no idea. Mark it, keep going, because the majority of questions your students are going to be able to answer if you've prepared them well. And that's what we want, because the number of questions they get correct, not the questions they get wrong. And so they need to review all the questions that they know they can answer and they're pretty confident about. That's a necessity. The other way to look at this is that you may have students every student's going to be different. So encourage them to find what works for them. If it's a math question, they want to save those to the end because they know it's going to take them a while. Mark it, save it to the end, right? And so you have to create these comfortable areas for your students when they're taking the test. They need to know what to expect. They need to have the practice in place. That's 60% of their exam score. The other 40% is coming from the FRQ questions. They have 90 minutes for 3 questions. However, 3 questions sounds nice because it's really more like 27. So there's 10 points per question. So that means there's 30 points altogether. It could be any topic, you name it, it could be possible. And this is, like I said, 40% of the exam score. Let's keep going. And so just in strategies in general. So if I'm talking to my students, please share this, please modify this, but you're teaching your students how to do this and be comfortable. Read the entire question. Be cautious. Did you read it correctly? Because I just got back from the AP reading, guys, and the number of students who gave me an energy source and instead of an energy user. So for example, if I think I actually said that backwards. So if I'm asking, for example, what's an energy source and someone says solar panel, that's not a source of energy, right? But the number of times I could not give a point because someone did that. And that's an easy one to kind of mix up. And so give your students specific examples if you have them. If you don't, then contact us and we'll be happy to help you. Happy to help you. But be cautious. Make sure you read it correctly. Answer the question to the best of your ability. This is actually advice from April, which I think is brilliant. Answer questions without reading the possible answers. This is a good idea because once you start reading those answers, well, they all start sounding a little bit good, right? So I would always try to get an answer in your head first because you teach your students to trust themselves, and that helps. Eliminate obvious incorrect answers. It's going to be something that's going to be a little bit funky, and yes, let's discard that one. Usually the correct answer would not be one of the absolutes. I think we recognize this as adults. Students don't always, so teach them that. And that's kind of funny. Be cautious of similar terms. We know the difference between these two terms, hopefully. But again, this was actually on the question I graded this year. They don't know the difference, guys. And this is one of those things that I think was really, to me, it's pretty straightforward, and my students usually get it, but I do emphasize it. And so the number of students who called biomagnification bioaccumulation on the question I was grading it's almost every other paper. And that was phenomenal to see. So be very cautious with similar terms. And then if you're unsure, like I said, I've already tagged it. I would go ahead and make an educated guess just in case there's not enough time for you to go back. So pay attention to your time as like teacher students to look at that. Tag for review. You might make some notes on scratch paper about some beginning thoughts, but yeah, make sure you have time to go back. I have students who was like, well, I've tagged it, but I'm going to go ahead and put what I think the answer is because then I don't have to write anything down. I'm like, okay, that makes sense. So again, get your students to trust their method, to practice their method, and it'll go well. Next slide. And so here's just an example. We want to give you an example of what this might look like in FRQ form with some of the embedded figures that you need to know. This is a standard soil texture trial question. However, it's not just the basic knowledge, there's also the application part. And so if you read through this very quick, we're talking about being able to use the skills to read the triangle correctly, but then being able to interpret what this means. And obviously, for anybody who's done this before, you don't actually need to go through and figure this out because it tells you it's 65% sand. It's clearly the biggest portion. So you don't even have to go through the whole process if you don't need to. What does sand do? Well, it allows things to filter through because of the high porosity, right? And so this is to me a pretty easy question, but this is going to trick some of your students up and they're going to waste their time trying to figure something out that they actually need to. So College Board is not afraid of giving extra information and figures that is not needed. And so obviously the answer to this question is B. But it's a good example of what they might face along with a figure. All right, next question, please. Let's talk about the FRQs. And so here are your 3 known questions that they're going to ask you guys. And so designing an investigation, analyzing the environmental problem and providing a solution, and then doing that same thing with embedded math. And so there's no question what they're going to have to do. We don't know what content is going to be embedded in this design, but we know what skills we need to practice to get them here for the most part, right? Next slide. So the first one is, and I'm giving just a little bit of backstory on each one. So designing an investigation. So obviously your students need to know the difference between IVs and DVs, controls, constants. They should be able to identify a hypothesis, and it could be a table with a little bit embedded backstory that they're given. So there's going to be something they have to pull out the information from what's given. I still see people confusing IV and DV all the time, all the time. Controls, constants. For some reason, that's always mixed up. So this should be like that drill. We know they're going to get this question. We know they're going to be asked at least some of these concepts. Let's do this, right? So the describe part, there's usually something about the data that they need to describe. So using the given data, not something that they know about the content that's probably correct, because that may not be the answer to the question. Based on the given data, oh, I think this because of this, right? That's what I mean by describe. You need to give me a reason. The explain is usually kind of going to come in the concept of, okay, well, here's the experiment was designed, and you've already told me what you think the outcome's going to be. But what if instead of this experiment, this happened? And suddenly your student has to shift gears and go, okay, wait, So if that's now this, remember, so they're thinking through, they can't see it, it's not written, they can't read through that. They have to apply this chunk back into the original. Okay, what's going to happen now? Can they predict that? This needs to be practiced as a concept, right? Again, we know this is going to be asked of them, so let's make sure we do it. Next slide. This is FRQ2, proposing a solution. You're going to have an environmental problem first. And so this will include topics from multiple units. I always find it interesting how College Board weaves together different unit questions, because suddenly we're talking about wind patterns, and then we're talking about water purification, and then it's like, I don't even know anymore. It's always very good. The key thing with this is you have to pay attention to the task verbs. Are you identifying? Are you explaining? Are you describing? And then my biggest thing is, I've already said this, but please answer the question that's given, not just based on your content knowledge, but the actual given scenario, the given data, right? Because that is a different answer. And then avoiding vague terms. Try to be as specific as possible, because if it's a vague term, I can't infer as a reader. I can't assume that you know it. And so this goes back to you as a teacher preparing them. Be brutal. Don't give them points for almost, right? All right, keep going. The FRQ number 3 is basically the same thing, but this is where that embedded math is. And you have to show your setup. If you don't practice this, it's bad. It's really bad. So College Board does offer a guide for entering the calculations. It could be better. The nice news is that is something they are given on the exam. I'm not sure if that's going to happen forever, but that is something that we're giving them that same entering calculation practice sheet. And so please give that to them to practice. Please clarify that if they don't show parentheses around order of operations, then they're not going to get the point, because you're not going to get the same answer. For example, and I think we can keep going, I can give you another example on this. Yeah, keep going. Okay, we're gonna skip this one for time purposes. And then when
I
I
think,
get to
Erica,
math,
if we can, let's jump to the math piece
Wanna
that
get
you're
to the math?
thinking of.
Okay.
Yeah. Let's jump to math, because I saw some comments about that in the chat.
Okay. So really, really quick. What we skipped was some resources that you guys can go back and look at. Specifically, someone mentioned task verbs in the chat. So there's a resource for that you can use to teach your students what those mean. So here's all our mathematical routines. I will remind you guys, it's a science practice 6. It's 12 to 13% of the entire exam. So you can't skip out teaching the math concepts. I've heard teachers say that, well, this math is pretty easy, they should be able to do it. Oh, that's a lot of points, guys. So about 5 to 7 questions are going to be math and the multiple choice. 6 of the 10 points on question number 3 are going to be math. You get a point for showing the correct setup with units. You get a point for the correct numerical answer with units. And I don't tell my students this, but the units are not required if in the answer if it was given in the prompt. So I'd always say, guys, put your units. You do not get a formula sheet, but if programmable calculators are still required, sorry, they're still permitted, but a lot of schools don't have them. My students don't have them, so they have to remember their formula. And so it's up to you guys if and want to invest in calculators, or College Board is working up to getting everyone to just use Desmos, which is the embedded calculator in Blue Book. We're just not there yet. So there's a slight equitable issue there, but let's keep going. There's a resource for math practice for you guys who are asking. Keep going. And then here's our reflection. And so we went through that fairly quickly. And so please let us know if you have any questions. But think about your own students right now. Where do you think they lose the points the most on FRQs? If you want to say something about MCQs, that's also fine. But type in the chat. If you're talking about MCQs, make your own format. If you're talking about FRQs, please type the number that corresponds to what you think they're getting wrong the most, or maybe confusing for them the most.
Perfect. FRQs are hard. It takes a lot of practice. It takes a lot of guidance from the teacher, right? And it takes a lot of understanding of the topic and how these things are related. Yeah, a lot of people saying vague general answers. And so I guess a question as I'm listening to all of this, a question for all of you teachers is when you have students who are latching on to environmental science, when they're showing an aptitude or an interest to continue studying, do you feel like you have resources to push them in the right direction? Where do you push students who are excited to continue in this? If you could drop that in the chat, that would be great. We'll take a look at that while you're going through. Perfect. Staking two concepts. Yeah, there's a lot going on. And so we designed these webinar series. We have two more coming up. Jillian, if you can jump to the slide that explains the next two sessions, that would be great. The next one is land and water use and energy resources. And the last one is global change. We sprinkled these throughout the summer. This is our first time doing this. Alexis and Colin, thank you again. It was fantastic. And I think I'm hearing from teachers on the side, chat, text messages and whatnot, that this has been really, really helpful. So please sign up for session 2 and session 3. The info and registration is on the QR code there. And we'll follow the same format. So we'll do content and then we'll do practical. What does this mean in the classroom? And for this first one, we kicked it off with sort of the big picture understanding of the test and how to take that, because some of you are new to the AP Environmental Science course and exam. But as we move through, we'll also help you tie this content directly to the FRQs. Erica did a great job of showing some of that in here. And so come to the next two. We will send out the recording, share it with your friends. We are also going to send you, if you attended, which all of you here did, if you're watching the recording, unfortunately, this doesn't apply to you, but we will send you your professional development certification so that you can log these hours, turn them into your administrator and work towards your goals there. But as we wrap up, any questions, or Alexis or Colin or Erica, any final comments that you want to jump in? I want to make sure everyone can sign off and enjoy their Monday afternoon right on time. But anything else anyone wants to add here? Drop your last questions or comments in the chat, if so. Yes, Christina, we're going to send the PD credit to your email address. So we've got that you were on and you'll get it that way. Okay, incredible. Well, for all of you, we are so glad that you attended. We've got slides to send out for sure. I'm Megan. If you've got questions, you can send it to me. That should be .org. I'm just going to go ahead and add that in if it updates in real time or not. But megan.morgan@switchon.org. And I'm putting, Alexis, thank you again for sharing and encouraging people to reach out. So generous of you. I'm putting that in there as well. And we'll file up with Chris and April and Erica's email addresses as well. If you would like to reach out to them, we have an email address through Switch Classroom where you can talk to them there as well. April with a question about internships. Yes, but can't sit still.
Yeah, I can try to pull some resources together. I don't know how much there is for high school students, but by the time they get to college, there is a lot of summer opportunities in earth and environmental sciences. Everything from NSF funded research experiences to full programs where they go study on a glacier for a summer. There are so many opportunities for students. So I'll see what I can
If you
find.
would do that, I would love you forever because I teach like 170 kids a year, environmental science, and I'd say 50 to 60 every year come and ask me, and I'm like, I don't know. So
Yes,
they're
I
headed.
will.
So
I'll see what I can pull together. Yeah.
thanks.
And I will also offer myself if anyone wants me to come to your classroom. If you're somewhat local to Denver, I would be happy to, come into your classroom and talk about what I do, or set up a Zoom something. I'd be happy to do that. I have benefited in my classes from having scientists that were doing really cool things Zoom in, and if I happen to be in the field that day, I can Zoom in from the field. And so we can set up some opportunities for students to ask questions and to kind of see, what it is that we do. So
Alexis, I know not everyone has their camera on, but I just felt like the World Wide Web pulse when you said that. Like 55 people just jumped out of their chairs, so excited to connect with you and have you join their classes.
We'll have to get a schedule going.
Incredible.
We can also do local to Dallas.
Yeah,
Texas.
There
Colin
you
is
go.
local to
Collins in
Dallas.
Dallas.
Yeah.
There were
Yeah.
a couple
So,
Texas folks on the
Yep.
call.
so
Incredible. And I'll just put it out there that when Alexis and I started talking about, we started wondering, hey, what could this look like in future years in person? So this year we're starting virtual. If that's something that you're like, oh my gosh, yes, I would come to Colorado in the summer, just drop me a note. I'm just gathering data at this point, but I think the response is strong. And if we can make something work, we might be able to do that in years to come. All right. With that, I think we are going to stay on for the last few minutes. If you've got any last minute questions, feel free to chat those. Otherwise, we wrapped up our programming just in time, so go ahead and enjoy your Monday. Thank you for joining us, and give us a couple days to pull everything together and send it out to you. Bye, everyone.
Hello,
Hi,
can you
Jessica.
hear me? Hi.
Mhm.
So I'm leaving teaching AP Environmental because I'm actually leaving high school level and going to middle school next year.
Yeah,
But I will be doing Earth. So, but I will be also helping train science teachers in my county. So I guess I was wondering what resources you have for sixth and seventh grade.
perfect. Which county or which state are you in, Jessica?
Georgia.
Okay, yeah, we do. We have Switch Classroom resources are mainly fourth grade through 12th grade. And so we have plenty available for you that ties in with sort of middle school general science, and you can pull in any way. So if you hop on the Switch Classroom website, you'll be able to explore by topic. And then each topic has an introduction level and a science of level. And that introduction level is probably your sweet spot for the middle school crew that you'll be teaching. But feel
Okay,
free to
awesome.
reach out if you're looking for something specific and you can't find it. Either it's in development or it's probably coming up next if it's not already up there.
Okay, thank you so much.
Yeah, no problem.
Have a good day.
You too.
Hi, I was just trying to make sure it's because I'm gonna be on the road, specifically on flight that day of the training on the 21st.
Mhm.
But more than likely I'll be arriving in Seattle hopefully at 10:30. So I'm like, maybe I can sign in on my phone and still catch a glimpse of the training. And then funny enough, the last session that you offer is when I'm going to be coming back. So,
Oh,
so yeah, I'm just gonna try to see if I can squeeze in as much as possible. But it's very informative. I liked it so much, especially the resources, the visuals, which always help a lot when trying to teach to my students to conceptualize and be able to kind of see how it ties in and not just individual topics. But
yeah.
thank you so much.
I'm glad you're here, Joyce. And there will be a recording for the other one. So if your flight is delayed or anything like that, we've got you covered. You can still watch it later.
All right, thank you.
Yeah, have a great summer.